By the time you look at scales of hundreds of millions of light years, the universe should appear smooth and uniform. Any given volume of space that large should contain roughly the same amount of matter as any other volume. The Hercules Corona Borealis Great Wall challenges this uniformity directly. It creates a massive concentration of matter along one direction in space. If you examine a volume 10 billion light-years long in the direction of the Great Wall, it contains far more matter than a volume of the same size in a perpendicular direction. The universe is not uniform at that scale. It has preferred directions and preferred locations. Some physicists argue this does not necessarily break the cosmological principle. They suggest the Great Wall might be a local anomaly. If the observable universe is large enough and you allow for statistical variations, occasionally you should see unusually large structures. These would be rare, but rare things happen sometimes. The universe could still be uniform on average, even if individual regions show extreme variations. This argument weakens when you consider the other large structures discovered in recent years. The Sloan Great Wall, the quasar clustering, the massive cosmic voids. Each discovery adds another example of the universe showing structure at scales where it should be uniform. If these are all rare statistical flukes, we are incredibly unlucky to be observing during a time when multiple flukes appear in our surveys. More troubling is the alignment problem. Several large-scale structures appear oriented along similar axes. They are not randomly distributed in all directions. They show preferred orientations. This suggests the universe might have large-scale structure even beyond what we can map directly. It hints at organization on scales approaching the size of the observable universe itself. If the cosmological principle is wrong, then many of our conclusions about the universe need revision. Dark energy estimates depend on assuming uniform expansion. The age of the universe derives from models assuming homogeneity. The Big Bang theory itself relies on the principle for most of its predictions. Questioning the principle means questioning the entire framework of modern cosmology. Yet the Great Wall sits in our data, confirmed by multiple observations, measured repeatedly. Real in every sense that matters scientifically. It exists, whether our principles allow it to or not. Redshift measurements confirm the Hercules Corona Borealis Great Wall exists at a specific distance, not scattered across space at different depths. When astronomers measure the redshift of galaxies or gamma-ray burst host galaxies along the Great Wall, they consistently get values between 1.6 and 2.1. This tight clustering of redshift values proves the structure occupies a defined region of three-dimensional space. Redshift works because the universe is expanding. As space expands, it stretches the wavelength of light traveling through it. Light that started out blue shifts toward red. Light that started out red shifts into infrared. The amount of shifting depends on how much the universe has expanded during the light's journey. Light from farther away travels longer and gets stretched more. Measure the stretch and you know the distance. The relationship between redshift and distance is not simple. You cannot just multiply redshift by the speed of light to get distance. The universe's expansion rate has changed over time. It was faster in the past when matter was denser. It accelerated in more recent epochs due to dark energy. Calculating distance from redshift requires accounting for this changing expansion rate, using the full framework of cosmology. For the Great Wall, redshift values between 1.6 and 2.1 translate to distances around 9 to 10 billion light-years. These measurements use the standard cosmological model that includes matter, and dark energy, in proportions confirmed by multiple independent observations. The uncertainty in the distance is relatively small, perhaps plus or minus a few 100 million light-years. That uncertainty does not affect the conclusion. The Great Wall is real and impossibly large. What makes redshift especially powerful is its precision. Modern spectrographs can measure redshift to accuracy better than 1 part in 10,000. This allows astronomers to determine not just that galaxies are far away, but exactly how far away they are relative to each other. Galaxies clustered in space will show similar redshifts. Galaxies spread across different distances will show a broad range of redshifts. The gamma-ray bursts defining the Great Wall show remarkably consistent redshifts. If these bursts were randomly scattered through space at different distances but happened to align from our perspective, we would expect to see significant variation in their redshifts. Instead, they cluster tightly around the same values. This consistency proves they occupy the same cosmic neighborhood despite being separated by billions of light-years across the sky. Some researchers attempted to explain away the Great Wall by suggesting systematic errors in redshift measurements. Maybe something about gamma-ray bursts or their host galaxies causes redshift to be measured incorrectly. Maybe dust between us and the bursts absorbs light in ways that mimic redshift. These proposals were tested and found lacking. Independent redshift measurements using different methods confirmed the original values. The consistency across multiple datasets rules out systematic errors. The precision of redshift measurements leaves no room for the Great Wall to be an illusion or measurement artifact. It exists where the data says it exists. At the distance, the data indicates. With the impossible size that follows from combining position and distance measurements, physics must explain it, even if current physics cannot. When confronted with something that breaks your models, you have three options: deny the observation, modify the models, or create entirely new physics. The astronomy community exhausted the first option. Multiple independent datasets confirm the Great Wall exists. That leaves modifying existing theories or proposing radical new ideas. One competing theory suggests modified Newtonian dynamics might explain large-scale structures better than general relativity. This idea, called MOND, proposes that gravity behaves differently at extremely low accelerations. In galaxy clusters and cosmic filaments, gravitational acceleration is incredibly weak. MOND predicts gravity becomes slightly stronger under these conditions than Einstein's equations suggest. Stronger gravity at cosmic scales would allow structures to form faster and grow larger. The Great Wall might be possible if gravity has a boost we have not accounted for. The problem is, MOND was designed to explain galaxy rotation curves, not cosmic megastructures. When researchers apply MOND to structure formation simulations, they get results that conflict with observations of the cosmic microwave background radiation. MOND solves one problem while creating several others. Another approach involves quantum gravity effects. Standard cosmology treats space as smooth and continuous. Quantum mechanics suggests space might have a granular structure at the smallest scales. Some physicists propose these quantum properties could influence structure formation in ways we have not calculated. Tiny quantum effects operating over billions of years might amplify into large-scale structures beyond classical predictions. This theory remains highly speculative. We have no experimental evidence for quantum gravity effects at cosmic scales. The mathematics is incomplete. The predictions are vague. It offers an interesting possibility, but no concrete mechanism for producing the Great Wall. A third proposal looks at the role of primordial magnetic fields. The early universe might have contained magnetic fields threading through space. These fields could have influenced how matter clumped together, creating preferred directions for structure formation. Magnetic fields can accelerate structure growth by channeling matter along field lines, potentially producing longer filaments than gravity alone would create. Computer simulations testing this idea show magnetic fields can enhance structure size by perhaps 50%. That helps, but does not bridge the gap between the theoretical maximum and the observed size of the Great Wall. You would need magnetic fields thousands of times stronger than any evidence suggests existed in the early universe. Some cosmologists propose the structure might have formed earlier than we think, before the epoch when standard structure formation began. If density variations existed in the universe before inflation, they might have been stretched to enormous scales during the inflationary period. These supersized variations could seed structures larger than normal quantum fluctuations allow. The challenge here is that inflation should erase any pre-existing structures. The exponential expansion smooths out variations, leaving only quantum fluctuations as seeds for later structure formation. Getting around this requires special conditions during inflation that have no observational support. Each competing theory attempts to explain the Great Wall by modifying one aspect of standard cosmology. None of them work completely. They either predict other effects we do not observe or require fine-tuning that seems implausible. The Great Wall resists explanation by simple modifications to existing physics. It demands something more fundamental. Between the galaxy clusters and filaments lie the cosmic voids. These regions contain very few galaxies compared to the universe's average density. Some voids span hundreds of millions of light years across. Inside them, you might find only a handful of small galaxies scattered through space that could contain thousands. The voids are not completely empty, but they are far emptier than theory predicts. Matter leaves voids for a simple reason. Gravity pulls it toward denser regions. Imagine a region of space that starts with slightly below average matter density. Nearby regions with average or above average density exert stronger gravitational pull. Matter at the edge of the low-density region feels this pull and starts drifting toward denser areas. As matter leaves, the void becomes even less dense. The process accelerates. Over billions of years, voids empty out while filaments grow denser. But matter does not leave instantly. The process takes time. Galaxies in voids still exist because they formed before the void emptied completely. These void galaxies provide clues about cosmic evolution. They evolved in isolation, experiencing fewer galaxy mergers than their counterparts in dense regions. Studying them shows us what happens when galaxies develop without constant gravitational harassment from neighbors. The space inside voids is not truly empty. It contains dark matter, diffuse gas, and dark energy. The dark matter forms tenuous filaments even within voids, though much less dense than the major cosmic filaments. Gas inside voids remains extremely thin, often just a few atoms per cubic meter. This gas is difficult to detect, but plays a role in the overall matter budget of the universe. Dark energy dominates inside voids. In dense regions, matter and dark matter exert significant gravitational influence, despite dark energy being present. Inside voids, with matter spread so thin, dark energy's repulsive effect faces little opposition. This causes voids to expand faster than the universe's average expansion rate. They grow larger over time, pushing surrounding matter into denser filaments. The Great Wall creates enormous voids on either side of its structure. If the Great Wall is 10 billion light-years long and contains concentrated matter, then adjacent regions must have below-average density to maintain the universe's overall average density. These voids might be equally massive, equally anomalous, but far harder to detect because empty space reveals itself only by the absence of light. Mapping these voids requires surveying huge volumes of space and noting where galaxies should be but are not. This is like trying to map holes in Swiss cheese by counting the cheese. You need complete surveys covering large areas. The voids adjacent to the Great Wall sit at distances where our surveys become incomplete. We see hints of vast empty regions but cannot map them precisely. What happens to matter over billions of years in such voids? It becomes increasingly isolated. Void galaxies burn through their gas, form their stars, and eventually go quiet. No new gas falls in to fuel fresh star formation. The galaxies fade to red as their bright blue stars age and die. Eventually, these galaxies become nearly invisible, containing only old red stars and stellar remnants. The voids grow, the filaments concentrate, and structures like the Great Wall become more extreme over time. The cosmic microwave background radiation is the oldest light in the universe. It comes from 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. This radiation fills all of space, coming from every direction at once. It provides a snapshot of the universe in its infancy. Telescopes measuring this background radiation find it remarkably uniform. The temperature is 2.7 degrees above absolute zero in every direction. Variations in temperature across the sky amount to only about 1 part in 100,000. This uniformity confirms the cosmological principle. The early universe was incredibly smooth, but those tiny variations matter enormously. They represent the seeds of all structure we see today. Slightly warmer spots indicate regions with slightly higher matter density. Slightly cooler spots indicate lower density. Gravity amplified these variations over billions of years. Dense regions became galaxy clusters. Low-density regions became voids. The temperature map of the cosmic microwave background is a baby picture of the cosmic web. Scientists have mapped these temperature variations with extreme precision. Satellites like WMAP and Planck measured the fluctuations to accuracy better than 1 part in a million. These measurements show that initial density variations were tiny, too tiny to produce structures as large as the Hercules corona Borealis Great Wall through normal gravitational growth. The size of variations in the cosmic microwave background correlates directly with the size of structures that can form. Larger initial variations produce larger final structures. The maximum variation size we observe in the background radiation predicts structures should not exceed about 1.2 billion light-years. This prediction matches computer simulations perfectly. It matches most observations of cosmic structure well, except it fails to predict the Great Wall by a factor of 8. Some researchers searched for anomalies in the cosmic microwave background that might explain unusually large structures. They looked for regions with stronger than average variations. They analyzed the pattern for unexpected features. They found a few interesting anomalies, including something called the cold spot, an unusually large, cool region that might indicate a supervoid. But nothing in the background radiation predicts a structure as large as the Great Wall. The absence of corresponding features in the cosmic microwave background creates a serious problem. If the Great Wall formed from initial density variations, those variations should leave clear signatures in the background radiation. We should see an elongated region of slightly higher temperature stretching across 10 billion light-years of the early universe. We do not see this. The background radiation shows no indication that seeds for such a massive structure existed. This suggests two possibilities. Either the Great Wall did not form from initial density variations, which contradicts our entire understanding of structure formation, or something happened between the cosmic microwave background era and the present that created structures from processes we do not understand. A third possibility is even more disturbing. Maybe the features are there in the cosmic microwave background, but we have not recognized them. Perhaps they appear in patterns we dismissed as noise or statistical fluctuations. If so, we have been looking at evidence of the Great Wall since we first mapped the background radiation. We just did not know what we were seeing. Computer simulations of cosmic structure formation are remarkably successful. Start with the conditions of the early universe as measured from the cosmic microwave background. Add the known amounts of normal matter, and dark energy. Apply the laws of gravity. Let the simulation evolve forward through 13.8 billion years of cosmic history. The result matches reality. The simulations produce galaxies, galaxy clusters, filaments, and voids. The sizes and spacing of these structures align with observations. The timeline of galaxy formation matches what we see when we look at distant, ancient galaxies. The simulations reproduce the cosmic web in stunning detail. This success gives cosmologists confidence they understand the fundamental processes shaping the universe. Thousands of these simulations have been run on supercomputers worldwide. Researchers vary the parameters to test different scenarios. They adjust the amount of dark matter. They modify the strength of initial density fluctuations. They try different models for dark energy. They change the cosmological constant. Every variation produces similar results. Structures form and grow, but they cap out at approximately 1.2 billion light-years. No simulation has ever produced anything resembling the Hercules corona Borealis Great Wall. Researchers specifically tried to recreate it by optimizing every parameter for maximum structure size. They started simulations with the largest allowable initial variations. They boosted dark matter density. They minimized dark energy's effect. Even under these ideal conditions, the simulations created structures only about 1.5 billion light-years across. The failure is not subtle. The simulations missed the target by a factor of 6 to 7. This is not a small discrepancy you can explain by measurement uncertainty or computational limits. The simulations definitively predict that structures the size of the Great Wall cannot exist, yet observations definitively show they do exist. Some researchers questioned whether the simulations might be missing important physics. Maybe gravitational calculations break down at cosmic scales in ways we have not noticed. Maybe dark matter has properties that only become important in the largest structures. Maybe there are feedback effects between normal matter and dark matter we have not included. Teams added more complexity to their simulations. They included magnetic fields. They modeled gas dynamics in greater detail. They incorporated the effects of black holes and stellar feedback. They tried alternative theories of gravity. None of these additions changed the outcome significantly. The maximum structure size remained around 1.2 billion light-years. The computational power behind these simulations is staggering. Modern cosmological simulations track billions of particles representing matter throughout the universe. They calculate gravitational forces between all these particles over billions of years of evolution. This requires some of the world's most powerful supercomputers running for weeks. The simulations capture physics at scales from individual galaxies up to the entire observable universe. Yet they fail to produce one specific structure we observe. This failure is more than an embarrassment. It represents a fundamental gap in our understanding. The simulations work everywhere else. They match countless observations. They predict the universe we see, except for this one glaring exception. Something creates the Great Wall through processes our best physics cannot simulate. Something we have not discovered yet. Gravity is the most thoroughly tested force in physics at small and medium scales. We know how it works between planets. We understand it for binary stars. We can predict the orbits of spacecraft with incredible precision. General relativity describes gravity near black holes and neutron stars with perfect accuracy, but cosmic scales are different. The distances are billions of light years. The masses are trillions of times larger than anything we can test directly. What if gravity behaves slightly differently at these extremes? Small modifications to gravitational strength at cosmic scales could allow larger structures to form without affecting smaller systems, where we have tested gravity thoroughly. This idea attracts physicists because it offers a potential solution to the Great Wall problem without overturning everything we know. One proposal suggests gravity might have a very small positive feedback effect at large distances. Normally, gravity weakens with distance following the inverse square law. Double the distance, and gravity drops to 1/4 strength. This relationship has been tested extensively. But what if, at distances beyond 1 billion light-years, gravity stops weakening quite so fast? A tiny deviation from inverse square, perhaps 1 part in 10,000, would be undetectable in normal tests, but could accumulate at cosmic scales. Stronger gravity at extreme distances would allow structures to pull together faster. The Great Wall might have formed in the available time if gravity provided just a small boost over billions of light-years. Calculations show you need gravity to be only about 2% stronger at cosmic scales to make the Great Wall possible. That is a small enough modification that it might hide within our measurement uncertainties. The problem is we have ways to test gravity at cosmic scales. Galaxy cluster dynamics show us how gravity behaves across millions of light-years. Gravitational lensing, where massive objects bend light from background galaxies, tests gravity across billions of light-years. The cosmic microwave background radiation constrains how gravity operated in the early universe. All these observations agree with standard general relativity. None of them show the 2% boost needed to explain the Great Wall. Another idea involves screening mechanisms. Perhaps gravity operates at full strength locally, but some effect screens or reduces it at the largest scales. This would allow local tests to give standard results while cosmic structure formation proceeds differently. Several theoretical frameworks propose mechanisms that could create this screening, usually involving additional scalar fields permeating space. These theories make predictions we can test. They affect how galaxy clusters behave. They influence the expansion rate of the universe. They change predictions for gravitational wave propagation. So far, observations have ruled out most screening mechanisms that would be strong enough to explain the Great Wall. The modifications required are either too large, affecting things we measure accurately, or too small, failing to solve the problem. A more radical possibility questions whether gravity alone governs cosmic structure. Maybe another force contributes at the largest scales. Perhaps dark energy does not just cause acceleration, but also has directional effects that enhance structure growth along certain axes. This would require dark energy to be more complex than current models assume. Testing these ideas requires pushing observations to their limits and comparing results against modified gravity predictions. So far, standard gravity keeps winning, except when it comes to the Great Wall. dark energy makes up about 68% of everything in the universe. It drives the accelerating expansion of space itself. Unlike matter and gravity, which pull things together, dark energy pushes everything apart. This repulsive effect grows stronger as space expands because dark energy has constant density. More space means more dark energy means stronger repulsion. Scientists discovered dark energy in 1998 by measuring distant supernovae. These exploding stars appeared dimmer than expected, indicating the universe's expansion was accelerating. Something was pushing space apart faster than gravity could pull matter together. That something is dark energy, though we do not know what it actually is. We only know what it does. The Standard Model treats dark energy as the cosmological constant, a property of space itself that remains the same everywhere and always. Every cubic meter of space contains the same amount of dark energy, regardless of whether matter is present. This simplicity makes calculations tractable, but might be wrong. Dark energy could vary across space or change over time in ways we have not detected. The Hercules Corona Borealis Great Wall challenges this uniform picture. If dark energy truly has constant density everywhere, then its effects should not create structures. It should push all matter apart equally in all directions. Yet the Great Wall exists, suggesting matter behaved differently in that region of space compared to others. Either dark energy varied there, or something else overcame dark energy's repulsive effects. Some cosmologists propose dark energy might interact with matter in ways beyond simple repulsion. Perhaps dark energy couples to dark matter or normal matter through forces we have not identified. These interactions could affect how fast structures form. In most of the universe, dark energy works against structure formation by driving expansion. But in regions with specific conditions, the interactions might enhance structure growth instead of hindering it. This would require dark energy to have structure itself. Instead of being perfectly smooth, dark energy might have variations in density or strength across cosmic scales. Denser dark energy would push expansion faster, creating voids. Less dense dark energy would allow matter to clump more easily, creating filaments and walls. The Great Wall might mark a region where dark energy density dropped below average for billions of years. Testing this idea is difficult. Dark energy reveals itself through its effect on expansion, which we measure by observing how fast distant galaxies recede. These measurements average over huge volumes of space. Detecting variations in dark energy density across different regions requires extremely precise measurements of expansion rates in multiple directions. Current data is not quite good enough. Alternative models suggest dark energy is not constant over time. Maybe it was weaker in the early universe and grew stronger more recently. Weaker dark energy in the past would have allowed structures more time to grow before accelerating expansion kicked in. The Great Wall might have formed during an epoch when dark energy was negligible, then survived into the current era when dark energy dominates. Observations of the cosmic microwave background radiation and the distribution of galaxies constrain how much dark energy could have changed over time. The allowed variation is small, probably too small to explain the Great Wall. Something about dark energy does not fit the standard picture. The Great Wall points toward complexity we have not accounted for. The Hercules Corona Borealis Great Wall is not the only anomaly found at cosmic scales. As surveys map deeper into space and cover larger areas of sky, other unexpected features emerge. Each discovery adds weight to the idea that the universe at the largest scales does not behave as our models predict. In 2004, astronomers identified an enormous void called the Eridanus supervoid. This region spans about 1 billion light-years and contains significantly fewer galaxies than average. What makes it especially strange is its connection to the cold spot in the cosmic microwave background radiation. The cold spot is an unusually large, cool region that should not exist based on standard cosmological fluctuations. The supervoid might explain the cold spot through a process called the integrated Sachs-Wolf effect, but the void itself requires explanation. Another anomaly appeared in 2007 when researchers found a cluster of quasars stretching across 4 billion light-years. Quasars are supermassive black holes actively consuming matter in the centers of galaxies. Finding them grouped together was surprising. Finding them aligned across distances exceeding theoretical limits was shocking. Debate continues about whether this represents a true structure or a chance alignment, but the pattern is statistically significant. The Shapley supercluster presents a different kind of problem. This massive concentration of galaxy clusters sits about 650 million light-years from Earth. It contains mass equivalent to about 10,000 Milky Way galaxies and spans 300 million light-years. The supercluster exerts enough gravitational pull to affect the motion of our own local group of galaxies. We are being pulled towards Shapley at about 400 miles per second. The mass required to cause this motion exceeds what we can account for by counting visible galaxies and estimating dark matter. Researchers mapping galaxy distributions found what they call the axis of evil in the cosmic microwave background radiation. This is a pattern where the largest temperature fluctuations seem to align along a specific axis through space. The cosmological principle predicts no such alignment should exist. The universe should look the same in all directions. Yet multiple independent analyses confirm the pattern. Some scientists dismiss it as statistical noise. Others see it as evidence of fundamental asymmetry in the universe. The Great Attractor poses another mystery. This is a gravitational anomaly in intergalactic space toward which hundreds of thousands of galaxies appear to be flowing. It sits roughly 150 million light-years away in the direction of the Centaurus and Hydra constellations. Visible matter in that region cannot account for the gravitational pull. Dark matter must be involved, but the concentration required seems too large to form in the time available. Then there is the motion of galaxy clusters themselves. Large-scale surveys show clusters moving in unexpected ways. Instead of random motions in all directions, many clusters appear to flow together in the same direction. This motion pattern, called dark flow, suggests the clusters respond to gravitational influences from beyond the observable universe. If true, this means structure exists on scales larger than we can see. Each anomaly can be explained individually with enough creative theorizing, but taken together, they paint a picture of a universe more complex and structured at large scales than standard cosmology allows. The Great Wall is the most extreme example, but it is not alone. If the Hercules Corona Borealis Great Wall exists, logic suggests it might not be unique. The observable universe spans about 93 billion light-years across. We have mapped only a fraction of this volume in the detail needed to find structures like the Great Wall. Most of our deep surveys cover narrow slices of sky. Vast regions remain unexplored at the distances where the Great Wall sits. Discovering the Great Wall required 15 years of gamma-ray burst data covering a specific patch of sky. Obtaining similar data for the entire sky would take centuries at current detection rates. We may have found the Great Wall because we happened to survey the right region at the right depth. Other structures of similar size could exist in areas we have not examined thoroughly. This possibility disturbs cosmologists. One structure pushing theoretical limits might be a rare statistical fluctuation. Multiple structures would indicate something systematically wrong with our models. If the universe routinely produces formations 8 times larger than physics predicts, then our understanding of cosmic evolution is fundamentally incomplete. Some researchers calculated how many structures like the Great Wall might exist in the observable universe if they form through rare but possible statistical variations. The calculations suggest perhaps 2 to 5 such structures should exist throughout all of space. We have potentially found one. That leaves 1 to 4 others waiting to be discovered. If surveys eventually find multiple Great Walls, it confirms they represent extreme but natural outcomes of cosmic structure formation. But if we find more than 5, standard statistics breaks down. Too many extreme outliers suggests they are not outliers at all, but rather normal features we failed to predict. The theoretical framework would require major revision. Early searches in other regions of sky have found hints. There are concentrations of gamma-ray bursts in areas that might indicate similar structures at similar distances. None yet confirmed with the same statistical significance as the original Great Wall, but the patterns are suggestive. More data over more years will clarify whether these hints represent real structures or noise. The implications extend beyond cosmology. If structures this large are common, they affect estimates of the total matter content of the universe. They influence calculations of dark matter distribution. They change predictions for how galaxy formation proceeded over cosmic history. Multiple great walls would mean significant fractions of the universe's matter concentrate in these megastructures, leaving even larger voids between them. This would create a universe far more clumpy and irregular at the largest scales than current models assume. The cosmological principle would fail not just locally, but globally. The universe would have vast regions with very different properties depending on whether you sit inside a great wall structure or in the voids between them. For intelligent life, this matters. Galaxy formation rates differ between dense structures and voids. Star formation proceeds differently. The chemistry of planets forming from different stellar generations varies. If great walls are common, then the conditions suitable for life might concentrate in or around these structures. Or perhaps life thrives better in the calmer environments of voids. We do not know because we barely understand these structures exist. Finding multiple structures, like the Great Wall, would tell us our cosmic neighborhood is more chaotic and extreme than we ever imagined. The search continues across the sky. The cosmological principle relies on the idea that the universe has no preferred direction. Look north or south, east or west, up or down, and the universe should appear statistically the same. Galaxies might cluster differently in each direction at small scales, but average over large enough distances and the density should even out. This isotropy is fundamental to how we model cosmic expansion and evolution. The Hercules Corona Borealis Great Wall violates this assumption directly. It creates a massive density enhancement along one specific line through space. Point a telescope toward the Great Wall, and you see far more matter than average. Point 90 degrees away, and you see less. The universe demonstrably does not look the same in all directions when you include structures this large. Some cosmologists argue this does not truly break the cosmological principle, because the principle only needs to hold when averaged over scales larger than the largest structures. If the Great Wall represents the biggest thing in the universe, then averaging over scales of 20 billion light-years or more should restore uniformity. The problem is, we cannot observe scales that large. The observable universe only extends about 46 billion light-years in any direction from Earth. This limitation means we can never test whether the cosmological principle holds at scales larger than the structures we observe. We assume it does, based on theoretical arguments, but we have no direct evidence. The Great Wall forces us to question this assumption. If structures 10 billion light-years across exist, what prevents structures 20 billion light-years across from existing, or 50 billion light-years across? The observable universe might be too small to capture the universe's true large-scale structure. We could be living in a region that appears smooth at scales we can measure, but actually sits within much larger structures we cannot see. This would be like trying to understand Earth's geography by examining a square mile of Nebraska. You might conclude the planet is flat grassland, stretching infinitely in all directions. You would be wrong, but you would have no way to know. The alignment of large structures suggests preferred directions might exist. The axis of evil in the cosmic microwave background radiation aligns with other large-scale features. The Shapley concentration, the Great Attractor, and several galaxy filaments show correlations in their orientations. These patterns could be coincidences, or they could indicate the universe has large-scale structure affecting everything within it. If the universe has preferred directions, many cosmological calculations become invalid. The equations describing cosmic expansion assume expansion is the same in all direction. They assume no center, no edge, no axis. Preferred directions would mean the universe expands faster in some directions than others. Galaxies would age at different rates, depending on their location and orientation. The cosmic history we have reconstructed from observations might be correct for our local region, but wrong as a description of the universe as a whole. This possibility opens uncomfortable questions. Where is Earth in this larger structure? Are we in a typical region or an unusual one? Do the physical constants we measure here apply everywhere? How much of our cosmology is local knowledge mistakenly applied universally? The Great Wall suggests we might be asking the wrong questions about the universe because we cannot see enough of it to ask the right ones. Next-generation telescopes will map the universe with unprecedented depth and coverage. The James Webb Space Telescope, already operating, peers deeper into space and time than ever before. Ground-based observatories, like the Vera Rubin Observatory, will survey the entire visible sky repeatedly, cataloging billions of galaxies and tracking how they evolve. The Square-Kilometre Array will map neutral hydrogen across cosmic history, revealing structure in regions too distant for optical surveys. These instruments will specifically search for more structures, like the Hercules Corona Borealis Great Wall. They will map gamma-ray bursts with better precision. They will survey larger areas of sky to greater depths. They will measure redshifts for millions of additional galaxies, building three-dimensional maps of cosmic structure back to when the universe was younger than 2 billion years old. If more Great Walls exist, these telescopes will find them. If the original Great Wall is unique, that uniqueness will become apparent as surveys cover more of the observable universe without finding similar structures. Either outcome teaches us something fundamental about how the cosmos works. The observations will also test specific predictions. Modified gravity theories make detailed forecasts about how structure should appear at different distances and scales. Dark energy models predict specific patterns in how galaxies cluster. Alternative cosmologies suggest different distributions of voids and filaments. Next-generation surveys will have enough statistical power to distinguish between these possibilities. One critical measurement involves the cosmic microwave background radiation at higher resolution. Current maps resolve temperature fluctuations to about 5 arc-minutes, roughly 1/6 the width of the full moon. Future missions might achieve resolution 10 times better. This would reveal smaller-scale patterns that could indicate the seeds of structures like the Great Wall. If those seeds do not appear in the background radiation, it definitively rules out the Great Wall forming from initial density fluctuations. Gravitational wave astronomy adds another tool. Future space-based gravitational wave detectors will sense mergers of supermassive black holes across the observable universe. These black holes sit at the centers of massive galaxies, which concentrate in structures like the Great Wall. Mapping black hole merger rates in different regions of space tells us how galaxy density varies at cosmic scales. High merger rates would indicate dense structures. Low rates would mark voids. The telescopes will also track cosmic expansion more precisely by measuring distances to many more supernovae and other standard candles. This improves our understanding of dark energy and how it evolved over time. If dark energy variations contributed to forming the Great Wall, better measurements should reveal patterns in expansion rates that correlate with large-scale structure. Surveys will map the distribution of dark matter using gravitational lensing. Massive structures bend light from background galaxies in measurable ways. By analyzing millions of lensing events, astronomers build maps showing where dark matter concentrates. These maps will reveal whether dark matter forms structures as large as the Great Wall, or if the Great Wall is primarily normal matter distributed unusually. Perhaps most importantly, next-generation telescopes will observe the universe at epochs we have barely explored. They will see the first billion years after the Big Bang in detail, watching how the earliest structures formed. If the processes that created the Great Wall operated differently in the early universe, these observations will show us how. We are entering an era where observations will outpace theory. Telescopes will find things we have not predicted. They always do. The universe began in a quantum state. At the moment of the Big Bang, everything was so small and dense that quantum mechanics governed its behavior. Tiny quantum fluctuations, uncertainties in the position and energy of particles, existed throughout this primordial state. Then cosmic inflation occurred. Space expanded exponentially fast, stretching these quantum fluctuations from subatomic scales to cosmic dimensions. These stretched fluctuations became the seeds of all structure. Regions where quantum uncertainty created slightly more energy turned into slightly denser patches of space. When inflation ended and normal expansion resumed, these density variations remained frozen into the fabric of space. Gravity then spent billions of years amplifying them into galaxies, clusters, and the cosmic web. We can still see these quantum seeds today. They appear as temperature variations in the cosmic microwave background radiation. The pattern is random, as expected from quantum fluctuations, but it follows statistical rules determined by the physics of inflation. Analyzing these patterns tells us about conditions during the first fraction of a second after the Big Bang. The connection between quantum fluctuations and large-scale structure is one of cosmology's greatest triumphs. We can trace the history of specific galaxy clusters back to quantum events happening when the universe was 10 to the power of minus 35 seconds old. The mathematics works. The predictions match observations, except for structures like the Great Wall. Quantum fluctuations during inflation should create density variations with a maximum size determined by how long inflation lasted. Inflation probably continued for about 10 to the power of minus 32 seconds. This duration limits the size of fluctuations to scales that grow into structures no larger than about 1.2 billion light-years. Longer inflation would create larger fluctuations, but observations of the cosmic microwave background radiation constrain how long inflation could have lasted. Some physicists proposed that inflation might not have been uniform. Perhaps different regions of space inflated for different amounts of time. Areas that inflated longer would have larger quantum fluctuations stretched to bigger scales. These regions could produce larger structures like the Great Wall. The challenge is explaining why inflation would vary without conflicting with the uniformity we observe in the cosmic microwave background. Another idea involves multiple fields during inflation. Standard inflation models use a single quantum field to drive exponential expansion. Models with multiple fields can create more complex fluctuation patterns. These patterns might include rare, exceptionally large variations that seed megastructures. The mathematics becomes complicated quickly, and most multiple field models have been ruled out by observations. A more exotic proposal suggests the Great Wall might not come from quantum fluctuations at all, but from cosmic strings or other topological defects. These are hypothetical structures that might have formed during phase transitions in the very early universe, similar to cracks that form when water freezes. Cosmic strings would be linear defects threading through space, potentially seeding the formation of linear structures like the Great Wall. No evidence for cosmic strings has been found despite extensive searches. They should leave specific signatures in the cosmic microwave background radiation. Those signatures are absent. This does not completely rule out cosmic strings, but it makes them unlikely as an explanation. The quantum connection remains our best framework for understanding how structure forms, even if we cannot yet explain the Great Wall within it. The universe will continue expanding forever. Dark energy ensures this. As space expands, dark energy's repulsive effect grows stronger because its density remains constant while gravity from matter dilutes. Eventually, dark energy will dominate completely. Expansion will accelerate until galaxies beyond our local group recede faster than light, disappearing beyond an event horizon we can never cross. In about 100 billion years, the night sky will look very different. Most galaxies visible now will have moved beyond the observable universe. Stars will continue to form from remaining gas, but the gas supply is limited. Star formation will peak, then decline. After about 1 trillion years, no new stars will form. Existing stars will age and die. The universe will enter a dark era dominated by stellar remnants, black holes, and dark energy. The Hercules Corona Borealis Great Wall will play a role in this future. Its enormous gravitational mass will hold the structure together even as space expands around it. Galaxies within the Great Wall will merge over billions of years, forming larger and larger galaxies. Eventually, the entire structure might collapse into a single massive elliptical galaxy containing quadrillions of stars. Or perhaps a cluster of supermassive elliptical galaxies gravitationally bound together. This process depends on whether dark energy remains constant or changes over time. If dark energy strengthens, it could eventually overcome even the gravity of structures like the Great Wall, tearing them apart. This scenario, called the Big Rip, would end with every bound structure in the universe disintegrating, including atom. If dark energy weakens, gravity might regain dominance, potentially reversing cosmic expansion in a big crunch. Current observations suggest dark energy is likely the cosmological constant, remaining forever at its current strength. This leads to the heat death scenario, where expansion continues forever, entropy increases toward maximum, and the universe ends in a cold, empty, dark state. Structures like the Great Wall would be islands of matter in an exponentially growing void. But the Great Wall's existence questions whether our understanding of dark energy is complete. If dark energy varies in space or time in ways that allowed the Great Wall to form, those variations might affect the universe's ultimate fate. Perhaps dark energy is not truly constant. Perhaps it oscillates or follows cycles we have not detected because we have only observed for a tiny fraction of cosmic history. The structure might also affect local regions of space far in the future. Its gravitational influence will reshape trajectories of galaxies for hundreds of billions of years. Galaxy clusters moving through nearby space will be deflected by the Great Wall's mass. This could lead to unusual concentrations of matter or unexpected void formations, far from the structure itself. On the longest timescales, even black holes evaporate through Hawking radiation. After 10 to the power of 100 years, no black holes remain. The universe contains only photons, neutrinos, and possibly dark matter particles. The pattern of large-scale structure, including the Great Wall, will have dissolved completely, leaving no trace it ever existed. Yet during the universe's Middle Ages, the era when stars shine and galaxies cluster, the Great Wall stands as testament to processes we do not fully understand, a cosmic monument to the limits of our knowledge. The Hercules Corona Borealis Great Wall exposes cracks in cosmology's foundation. Every aspect of its existence challenges something we thought we understood. Its size violates theoretical limits derived from well-tested physics. Its formation timeline seems impossible given the universe's age. Computer simulations cannot recreate it. No modification to standard cosmology explains it without creating other problems. This does not mean cosmology is wrong. Our models work remarkably well for nearly everything we observe. They predict galaxy formation, cosmic expansion, the cosmic microwave background radiation, the abundance of light elements, and countless other phenomena with stunning accuracy. Cosmology ranks among humanity's greatest intellectual achievements. We have traced the universe's history from fractions of a second after the Big Bang to the present day. But the Great Wall tells us our models are incomplete. Something fundamental is missing from our equations. We might not understand gravity at cosmic scales as well as we think. Dark energy could be more complex than current models allow. Initial conditions in the early universe might have properties we have not discovered, or entirely new physics operates at scales we are just beginning to explore. The scientific method thrives on anomalies, like the Great Wall. When observations conflict with theory, we have two options: reject the observations if they prove faulty, or modify the theory to accommodate them. The Great Wall has survived repeated attempts at rejection. Multiple independent datasets confirm it exists. The measurements are solid. This leaves us with the harder task of modifying theory. History shows this process is not smooth. When Mercury's orbit disagreed with Newtonian gravity, physicists eventually needed general relativity to explain it. When galaxies rotated too fast, we eventually needed dark matter. When the universe accelerated unexpectedly, we eventually needed dark energy. Each discovery forced us to expand our understanding. Each seemed impossible until it became accepted fact. The Great Wall might be signaling the next revolution in cosmology. What seems impossible now, a structure 8 times larger than theoretical limits, might become the key to deeper understanding. Perhaps we will discover new properties of gravity. Perhaps we will find that dark energy has structure and variation. Perhaps quantum effects at cosmic scales are more important than we realized. Or perhaps the answer will surprise us completely. The greatest discoveries often come from directions nobody predicted.